All right, so we're here to talk about one-to-one and onto linear transformations. These two properties of being one-to-one and being onto are really properties about functions in general, but since all we're worried about in this course are linear transformations, that's the lens through which we'll view a function being one-to-one and onto. So just as a little bit of a reminder, I'm going to do this kind of in general, and then I'll explain. There's some nice things that happen for linear transformations with these two ideas. But let's first talk about just general functions. So if I have a function f, which maps the set D to a set E, remember that D is the domain. I shouldn't say equals, but D is the domain. And E is the codomain of the function. So E tells you what kind of values you can get out, but it doesn't have to be all the values that you get out. The set of all the values that you get out of the function is denoted f of D. And this is just the set of f of x, where x is in D. It turns out that that's always going to be a subset of E, but it might not be all of E. Okay, so the idea is that you have a function f, and this function is going to map some set D to some set E, and maybe it works out so that when you take all the values in D, what you get is not everything in E, but maybe you only get a little piece. Okay, so maybe all you get when you map D to E using this function f is maybe all you get is some little piece of E. This piece is the range of f. Okay, it's the values that you get from the function. E can really just be anything that has f of D as a subset. So anyway, so this is a general setup for functions that we've talked about before. Again, it's a little bit new, but we've talked about this in a previous video. And let's first talk about one-to-one. So we're going to say f is one-to-one if it has the following property. So f is going to be one-to-one if whenever you have f of a equals f of b, that forces to be true that a equals b. Of course, the other way around is always true for a function. If a is equal to b, then f of a is equal to f of b. In fact, that's the definition of a function, is that if you plug in the same value in the function, you're going to get out the same value. F of a and f of b will be equal if a and b are equal. But being one-to-one is the other way. So being one-to-one says that if you have two y values of your function that are equal, f of a and f of b, the only way that can happen is that if actually you have the same function plugged in for both. So, for example, I think a good starting example is if you were to look at the function mapping the reals to the reals given by f of x equals x squared. This is not one-to-one. Since you can find two different inputs, say 3 and negative 3, that have the same output, right? So here, this is not one-to-one since f of 3 and f of negative 3 are equal, but obviously 3 is not equal to negative 3. So you have two different inputs, in this case 3 and negative 3, giving you the same output. In this case, they're both 9, right? Because the function is y equals x squared. It turns out that f is one-to-one if and only if f passes the horizontal line test. So the vertical line test tells you it's a function. A horizontal line test tells you that this function is one-to-one. That's at least true if f maps r to r, right? So that's true there. It's a little bit harder to talk about the horizontal line test when your inputs are more complicated sets. But it turns out that if t is a linear transformation of two vector spaces, then this is nice. So if T is a linear combination, a linear transformation between two vector spaces V and W. Okay, so between the vector spaces V and W, then it turns out that T is 1-to-1. This is really the definition that we're going to work with. But T is 1-to-1 if and only if the kernel of T is just the zero vector. Remember, the kernel of T is just the set of all the values in V in the input. So it's the set of all, say, x in V, such that T of x is equal to 0. This is the zero vector in W. Okay, so that's the zero vector in W. So that's what it means for a linear transformation to be 1-to-1. Okay. That's again a theorem here. I don't really care too much to go through the proof, but let's think about just a few examples here. So let's say that our example is we're going to map, I just want to be consistent with the notation from the book here, but let's say that we're going to map T, so let's let T go from R2 to R2. Actually, I want to write it this way, where T of xy is equal to 3x plus y and x minus 2y. Okay, and so one of the things that we've tried to see before, one of the things that we've been talking about is finding the actual kernel of this linear operator. And so I'm going to leave that to you to find the kernel. But it turns out that there's a nice way that we can do this. So the kernel of T, what we can do is we're kind of putting all of these pieces together now. So this is going to be lots of things that we've done so far, just kind of grouped all together. So what we're going to do is we're going to take 3x plus y and x minus 2y and write this as being a product of a matrix and a vector. So we want to think of, and this is something that we'll talk about in some detail soon, it turns out that you can do this for any transformation regardless of what the two input vector spaces are. But if you have 3x plus y and x minus 2y, this is just taking the matrix 3, 1, 1, negative 2 and multiplying by xy, right? So you can just check that going from the right side to the left, that's what we get. And we know if we take the determinant of 3, 1, 1, negative 2, what that'll tell us is whether or not this function has a kernel that's 0 or not. So actually the determinant is really going to tell us, the determinant of this, what's going to be called a matrix transformation, or a transformation matrix, excuse me. But this determinant is going to tell us whether or not the linear transformation that we started with is 1-to-1. And the determinant is negative 7, right? Negative 6 minus 1. That's not 0. So this tells us a few things, and I just want to recall all the kind of equivalencies that we have here. But it turns out that since the determinant is non-zero, we know that the rank of this matrix, let's call this matrix A, just for convenience, but we know that the rank of A is 2, which means that the nullity of A, right, the dimension of the null space is 0, which means that the null space of A is just going to be the 0 vector, which means that the kernel of T is also just going to be the 0 vector, right? These are all equivalent definitions. We get all of that just from looking at the determinant. Okay, the determinant, again, is annoyingly useful, right? If we know the determinant of the matrix, then that tells us everything that we need to know. And since the kernel of T is non-zero, that tells us T is 1 to 1. Okay, so this is actually, you can already kind of check that this is going to give us another equivalent condition to the determinant of a matrix being non-zero. Okay. A few other things to say. So I want to just, again, quickly describe in general, for general functions, f going from d to e, f going from d to e is going to be called onto if, there's a few different ways to say this, but I think the easiest way, since we've talked about the codomain and the domain, and the codomain and the range, is just to say that a function is onto if the codomain is equal to the range, right? So if the codomain is equal to the range. And if that's the case, then our function is onto. Okay. It turns out, again, for linear transformations, that we have the following. So it turns out that if T is a linear transformation between two vector spaces V and W, so if T is a linear transformation for vector spaces V and W, then T is going to be onto if and only if, so if and only if the rank of T is equal to the dimension of W. Okay, remember that the rank of T, is the dimension of the image of T. Okay, and so a function is going to be onto if and only if the rank of T is equal to the dimension of that vector space W. And one more fact that's going to be very useful for us, it turns out that if T is a linear transformation for vector spaces V and W, just to save a little time here, I'm going to copy and paste that. Okay, so if if T is a linear transformation for the vector spaces V and W, then and if V and W have the same dimension, so if the dimension of V and the dimension of W are equal, then it turns out that T is going to be onto if and only if T is 1 to 1. In other words, if V and W have the same dimension, then T either has to be both 1 to 1 and onto, or neither. It can't be that it's one or the other. It's just that it's got to be either both 1 to 1 and onto, or neither 1 to 1 and onto. It can't be mixed. Okay, so that's a theorem. Again, I'm not going to get too much into the proofs here, but there we go. So that's the idea. And then the final definition for this video is if T going from V to W is a linear transformation, and if T is 1 to 1 and onto, then we have a special word for that. We call T, T is called an isomorphism. So isomorphism, kind of they have the same shape. That's really what that's trying to say. So then T is what's called an isomorphism. We could also say that V and W are isomorphic. Okay, so again, just meaning that they have the same shape. And one last fact here. So this is our last definition. So this definition is huge. We're going to talk about vector isomorphisms as we go along. But it turns out that if V and W are finite dimensional, so all the vector spaces that we've talked about over the course, including Rn, the set of at most n-degree polynomials, the set of matrices, these are all finite dimensional vector spaces. You could have an infinite dimensional vector space, say like the set of continuous functions. There's no nice way to talk about a basis there, at least not one that's immediately obvious. So all that we're talking about are finite dimensional vector spaces. So V and W are finite dimensional vector spaces. Then we're going to say that V and W, it turns out that V and W are isomorphic if and only if V and W have the same dimension. Okay, so if and only if V and W have the same dimension. Okay, and so that is everything I wanted to say about the definitions of isomorphisms. So one-to-one and onto linear transformations. And again, just to hit the highlights, remember that, let me scroll up here just for a second. Remember that T is going to be one-to-one if and only if the kernel of T is the zero vector, and T is going to be onto, if T is a linear transformation, T is going to be onto if and only if the rank of T and the dimension of W are the same. Okay, and if V and W have the same dimension, then you know that one is onto if and only if it's one-to-one. So it has to have both properties or neither, can't be mixed.